Yeah, I appreciate y'all's having me here today. Can y'all hear me okay? What I'm going to do, I've got a great panel here today, so I'm just going to spend a few minutes to sort of frame up the dialogue, get the discussion going, and then I'm going to turn it over to the panel members and let them each tell their stories. And then we'll open up the Q&A. First, just a quick reminder of why we're all here today. If you think about it, the NVMe journey really began because NAND flash emerged. That's really what started this journey. NAND flash emerged. Prior to that, it was an all-rotating world. It was SAS and SATA and SCSI. It was very well served by that. But NAND flash emerged and changed the paradigm. And then it was really Fusion IO who sort of showed us all that there was actually a performance benefit to getting the flash closer to the processor by putting it on the PCIe bus, and showed us that there was actually a business benefit from that people were looking for that kind of performance improvement. And so there was a business benefit to actually deliver that performance by getting PCIe flash, by getting flash closer to the server, and out from under the traditional SCSI, under the storage stacks. Of course, the original PCI adapters were that. They were flash adapters, which were great inside of the server as like a caching technology. But if you're really going to grow into a robust storage technology, you got to have standards. And so the first things to standardize were storage optimized standard form factors. And the two that are out there today are M.2, obviously, I think it's going to be fabulously successful in the client world. And then U.2, which is the 8639 connector, which is really emerging in the data center enterprise. And then finally, you need a standardized protocol. You can't have a storage infrastructure without a robust multi-party ecosystem, multiple suppliers, multiple devices, multiple vendors. So you need a standardized storage protocol, and you need standard operating system drivers. The original PCI flash adapters not only were on the PCI bus in a fairly limited form factor, but they were traditional proprietary form factors. So this has really been what's been driving the NVMe train for the last 4 or 5 years, but really this is just the beginning. If you look at this picture here in the lower left, I'm showing an M.2 SSD in a laptop computer or an NVMe flash adapter inside of a host server. And the key point of those slides is that I don't want to at all underestimate what it's taken to get to this point. Those particular embodiments of flash really are sort of in the PCI Express comfort zone. PCI Express was really designed as an inbox server connect for a handful of PCI slots. It was not designed as a storage capable infrastructure. And so if you really want to drive NVMe and PCIe storage out across the infrastructure, you have a lot of additional challenges that have to be overcome. And so the whole idea, look at that lower left, is sort of the NVMe nest. You've got PCIe storage, NVMe storage inside the server, a handful of locally attached devices. So what's it going to really take to push that beyond, to the edge of the server and then beyond? So the next picture in the lower left shows the first step, which Gary's going to talk about from Dell, which is just getting that PCI lanes off of the server motherboard and physically getting them cabled over to a mid-plane that allows you to have an externally accessible storage bay, which is the U.2 bay. And even that first step, just getting the PCIe flash to the edge of the server, actually took quite a bit of work. You had to figure out the internal cabling, there were management issues, there's hot pluggability and serviceability issues. So the first step of this journey is getting it off the flash adapter and to the edge of the server where it can actually be serviced. Then the two middle pictures there are really, once you've gotten the PCIe flash to the edge of the server, then how do you move PCI flash beyond the server? And those two middle pictures sort of show some of the things that were referred to earlier in the day, like the NVMe JBOF, where you have like a single server cabled to an external device shelf, or you actually have a modest number of servers, 2 servers or 8 servers, actually sharing a pool of NVMe devices over a low latency PCI interconnect. Those types of architectures, the industry is using the term rack scale architectures. And so those two middle pictures really represent like 2 servers sharing a pool of NVMe devices, or a sub-rack or a rack, 4, 8, 16 servers sharing a pool of NVMe storage over PCIe. And so that forces you into external cabling, it forces you into chassis management. You have a lot of issues you have to solve there. And then finally, the picture in the upper right sort of shows the end game, pushing NVMe really out into the realm of scalable enterprise class mission critical storage. which is, by definition, means it's shared by tens or hundreds or thousands of servers where you have a centralized storage asset. And it also means high availability, NVMe being deployed in topologies that do not allow for single point failure. And so Chris from Facebook and Don are going to talk about some of the rack scale architecture. And at the end, I'm going to turn it over to Ziv and to Tim to talk about NVMe role in external storage and mission critical external storage. And then these are just some of the challenges that the industry, the NVMe PCI ecosystem has to overcome on that journey. So the first one, you just got the basics, PCI Express signal routing, getting 4 SerDes and 25 watts to 1 or 2 or 4 bays is not that difficult. But actually getting to 10 bays or 24 bays or hundreds of bays, all of a sudden the signal routing and then all the power and cooling issues associated with that become a very daunting challenge. And then clocking, I think we'll all sort of breathe a sigh of relief once the industry finally gets distributed ref clock on PCIe in the rearview mirror, and we're all onto an SRAS world. So we really need to get to a modern clocking model across the industry. Cabling, we've already talked about inside the box, getting the PCI lanes off the motherboard to the edge of the server, and then beyond the box cabling. Hot plug serviceability, moving beyond PCI's original synchronous hot plug model to a true surprise insertion, surprise removal model. That's a lot trickier than it seems on the surface. Manageability, Amber talked quite a bit about this morning, moving from device manageability to bay manageability, and finally to enclosure manageability. And then I want to touch a bit on data protection. The industry is very aware that the traditional data protection strategies, RAID, or in hyperscale, you have a lot of distributed replication, distributed erasure codes. Extremely important aspect of robust storage, and but those data protection architectures really evolved in a HDD, a hard disk drive world. And SSDs at a device level just have this tremendous performance potential, but the data protection layers have to evolve in order to flow that innate device potential through to the end user applications. And so SSDs, performance potential of SSDs is really surfacing lots of bottlenecks that exist upstream of the device. And finally, I talked about high availability and dual domain topologies, which are in the realm of traditional mission critical external storage, and then sharing, going all the way from, so you sort of see the beginning and end. We talked about a handful of locally attached devices on a laptop or a server, eventually going all the way out to where NVMe is a successful technology, even in a highly scalable, broadly shareable storage infrastructure. And the last mention there is not really a technical challenge, but I think because M.2 is going to be fabulously successful in clients, just like SATA was successful in clients, that's going to trade a very, very significant economies of scale based on client technology. And so how can we take advantage of that economies of scale that's going to come out of the client world? How can we take advantage of that in the enterprise? So with that, I'm going to turn it over to Gary and talk about the first stage of this journey. Gary leads a team that is responsible for defining the strategy and architectures for the Dell Enterprise Server Group. He and his team are especially focused these days on solid-state storage and non-volatile memory, and either lead or actively participate in a bunch of relevant standards bodies, including NVMe, PCIe, T10, SFF, and SNIA. And prior to Dell, Gary held engineering and management positions at ST Microelectronics and Compaq. So with that, I'll turn it over to Gary.
Thanks, John. So, I went through the early days of bringing NVMe to the platform. So, whenever we were first playing with the first cards, these were cards from Fusion IO, and we saw that the performance that they had, we talked to our customers and tried to get their feedback about what did they like and dislike about the card. And the first thing that came up was serviceability. And so, the other consideration that we're looking at inside of the platform is not just the serviceability, but also industry adoption, who's going to be supporting these devices, as well as what are the standards around the drives that we're putting inside our platforms. Of course, we're very, very concerned about drive metrics and understanding what's the reliability, what's the performance, the whole laundry list. And lastly, how do we incorporate this inside of our platforms? In my case, especially in server. So let me give you a little bit of background on what we went through on the drive history. Again, starting with the Fusion.O card and understanding our customer needs, we realized that we had to make these devices serviceable. So what does that entail? So we needed to have front access, hot pluggability. It needed to be a form factor that was pluggable, as well as a connector that would support the hot pluggability. In this case, having staggered pin groups in order to enable that. And then lastly, the other part of the equation was, what about the protocol? So that would incorporate what would make sense for an SSD type device, because when you look at the current incumbent protocols such as SATA and SAS, they have a lot of history with rotating media. So we really wanted a much lighter protocol to make it much more efficient and a lower latency protocol. On top of that, we needed special management for these types of devices. So the end result was this 2.5 inch 15 millimeter form factor, 25 watt power envelope. And one thing I want to say about the 25 watts is that was non-standard for the 2.5 inch. But in order to realize the full value of the performance of NAND technology, we had to extend the power envelope range. At the time before that, it was 9 watts. So the connector, as I mentioned before, needed to be one that would be hot pluggable. And that led us to the 8639 creation, where we took essentially the current SAS connector, I think the 8680, thank you, and we added PCIe lanes, 4 of them, in addition to the existing 2 SAS lanes. And as well as we drove forward the NVMe protocol, working with others in the industry. So that the end result is that we have a high-performance PCIe device that is serviceable. And it's also backwards compatible with a 2.5 inch drive for SAS and SATA that were available. And along with that, we still include the higher performance that we were getting with the cards themselves. And we've been working with all of the OS vendors to have an open box driver to support that. And inside the platform, because we don't have to have bridge chips, we actually can have lower component cost inside of our platforms. So let's talk about the challenges that we had in NVMe. Now, first thing you're going to notice that I'm PowerPoint challenged, but I wanted to kind of point out what are the different connectivity points that we have for these types of devices. So at the top there, you see a direct connection to the processor, which is PCIe. We can also go through a PCI switch, which is really how we started out, where we had a card with a switch on it that we bridged over from the back of the server. And then lastly, we have the capability of doing a bridge shift. In this case, it would be a south bridge. So what I'm going to do is talk about some of the challenges that we went through and give a little bit of idea about what we expect to be the challenges in the future. So on performance balance, really what we wanted to do is understand the performance profile of these devices and how do we extract that. So we ended up doing a by-4 PCIe interface, and that gave us the best balance at that point in time. In the future, what we have to realize is that we're going to be looking at new types of non-volatile memory. We're going to be seeing changes in PCIe going from Gen 3 to Gen 4. And lastly, we expect different usage models around the applications themselves and how customers plan to use these. So going forward, we still want to maintain a level of balance to make sure that we get the best performance that we can out of NAND. So then let's talk about power and thermal. I mean, the power and thermal, it was really a challenge because going to 25 watts, you can imagine that the platform engineers weren't really too thrilled about having to cool it. But we went through that and we determined that it was actually solvable. And right now you'll see that inside of Dell servers we have up to 8 of these devices, and we can pull that with no issues. And in the future, what we expected is that we're going to see probably some level of management of power so that we get better efficiency across the performance of these devices. And that could range from a low-end server that has low performance needs and probably want to only expend a small amount of power to the very high end. And we think management of these devices is going to help us get there. So on the mechanical aspect, I think right now what we're doing is that we're looking at extending the number of devices that we have inside of our servers. And so that's going to entail backplane and cabling challenges of how we implement this to make sure that we can scale appropriately across our portfolio of devices. I should say portfolio of servers. And that brings us to system management. When we first started, we were basically using whatever protocol was available at the time. With PCIe storage, we were using ATA and SCSI, and we were leveraging the management protocols of that time. But the NVMe industry group just took it on themselves to form their own working group around management. So there's a lot of work being done in this area to make sure that we can manage these devices appropriately at the different phases from standby to active to actually going through maintenance phases of these devices when we have failure. The next area is serviceability. I think we touched upon the fact that these are hot pluggable. And so right now what we wanted to ensure is that whenever a customer utilizes these devices, and I mentioned about 3 connectivity points, is that he has the same consistent behavior no matter which connectivity point it's being derived from. On reliability, for the most part, whenever we started this, we leveraged the same metrics that we saw from SSDs. We had the 2 million power hours in TDF. But what was unique about these devices is that they're roughly 3 to 5 times faster than their SAS counterparts. And so because we wanted the same consistent experience for our customers about the number of events that they would experience, we bumped up the bit error rate to, we improved it to 10 to the minus 18. And on reliability, we also have challenges there in the future, in that these devices are going to become even higher performance. We'll be having more devices inside of our platforms, and we have to ensure that the reliability is maintained at a high level. The next one is availability, and this is in the form of RAID. We have software RAID today. We are seeing hardware RAID being available in the marketplace. And so we expect these to coexist depending on what the customer usage models are, whether he wants to go for a value in solution or high performance. In security, this is actually when we first started out, we didn't have a security protocol, but now the industry is driving towards the adoption of Opal Lite and Opal for these classes of devices. I'm going to jump over to coexistence with SAS and SATA and come back to it. On clocking, Tom already talked about, we start out with graph clock, we're moving to the SRIS. And so right now that's really managing this timeline transition, but also to managing what are the implementations that we go through the different phases between the different clocking methods. Resets, I think that's pretty straightforward. We have them. And dual port, I think, is one of the other interesting areas that we included the definition of dual port capability inside these devices. And we're starting to see our external storage array brethren adopting these devices, and they're the ones going to be permitted to take advantage of this type of capability. So let me go back to the coexistence with SAS and SATA. When we first started out, there was concern that we did have the availability of any multiplexing devices out there that could allow us to move between PCIe and SAS and SATA. So we eventually kept the lanes separate. And I think there's been a lot of questions in the industry about should we try to, merge the over-provision of lanes so we have SAS, SATA, and PCIe running across the same lanes. But if you look at the fact that we have 3 connectivity points, we came to the decision that keeping the lanes separate was still the best option for us, because if we didn't, whenever you want to have both stack SATA and PCIe coexist on the same slot, again, you have to go back to active components onto the backplane, which is an area that we want to avoid. So I've got to say that whenever we were challenged with bringing this type of device to the marketplace, we had a lot of work to go through. And I must say that the industry did a great job of rising to the challenge. And I remember back in 2011 sitting on a panel here with me and maybe one other counterpart that advocated PCIe storage. And I had 8 others that were advocating the incumbents. And I think a lot has changed over the past 5 years, so I think we've come a long way and they've done a great job. So I commend the industry for that. And I'll go ahead and turn it over back to Tom again for the next introduction. Thank you all.
Thank you, Eric. I'm going to turn the floor over to Chris Peterson from Facebook. Chris has been developing servers, storage, and data center solutions for over 12 years. He's worked on scale-up architectures, scale-out architectures, and containerized data center architectures. Chris has previous experience both with Dell and HP, but at this point in time, he is now spearheading the design and development of flash and non-volatile memory solutions at Facebook. So I will turn it over to Chris. Thank you.
Thanks, Tom. So when we at Facebook decided to build an open source PCIe-based flash storage system, we had a number of different system objectives in mind. So first of all, we wanted to build something that was both modular and flexible. And in this context, we were interested in being able to support a variety of different form factors. So that includes M.2s, U.2s, and even potentially 3.5-inch SSDs at some point. We also wanted to be able to tackle some of the upcoming workloads and changes in workload demands that we see at Facebook. And to be able to do that, we really have to have much better control over the compute to flash ratios in terms of resources. So part of the design was intended to be able to accommodate that as well. Secondly, we wanted to build something that was scalable. And in this context, we wanted to allow something that will scale in performance as the flash density has been increasing every 1.5 to 2 years. So we really wanted to have something that would allow us to maintain an IOPS per terabyte or bandwidth per terabyte as the density increases. And our existing solutions are just not able to do that. Finally, efficiency is always very important to us. So for us in our data centers, we want to be sure that every watt that we spend and every CFM that we spend is spent effectively. So all of our system designs really have to have that at the core of their design as well. So this is a high-level block diagram of the JBOF, or just a bunch of flash architecture. On the left, we have a dual-socket Xeon server. This could be any one of our normal servers, or it could be a single-socket server. It ultimately doesn't matter. But in this context, what we did is we added a low-profile PCIe card. On this PCIe card is a PCIe retimer. The purpose primarily of this card is to allow us to redrive PCIe signals from the server across external cables and into the JBOF itself. So the JBOF there is on the right-hand side of this picture, and the JBOF consists of a PCIe expansion board and a PCIe drive plane board. The active components live on the PCIe expansion board. So in this case, that is the PCIe switch itself and the BMC, which is the baseboard management controller. So the PCIe switch here provides the fan out from the server itself, or servers, back down to the downstream devices, the SSDs. So in our design, we have up to 32 lanes of PCIe Gen 3 coming out of the system. And we have the ability to connect those to up to 4 different servers. So that allows us, going back to my comment about flexible, it allows us to modify the number of compute resources that we have to the amount of flash in the system. The PCIe switch fans out to basically 60 lanes downstream. That can be set up as either 30 M.2s as by 2s, or 15 by 4s in a U.2 form factor. So some of the challenges that we ran into. So as I mentioned at the beginning, we wanted to build something that was based on open source and something that we could contribute back to the community as well. So one of the challenges with the existing Linux open source driver ecosystems is that a lot of the PCIe, hot plug, AR, NVMe drivers do not yet have a full handling mechanism in place for surprise hot plug. And surprise hot plug is really a key portion, as some of the other folks have already mentioned, to making NVMe actually viable in our ecosystems. You really want the systems to operate seamlessly in the same fashion you might expect a SAS or a SATA JBOD to operate. So we're in the process right now, and actually I found out today that we've already upstreamed a number of changes to the PCIe hot plug, AR, and NVMe drivers. The changes that we're implementing there are to make some bug fixes, as well as to make the drivers aware of PCIe all-at-once completions. A lot of that architecture has been in place for some time, but it hasn't actually been implemented in the Linux driver ecosystems. So those code changes are coming right now. That ultimately will improve the surprise hot plug scenario quite a bit because it really allows the drivers to become aware that the devices are no longer there and they can gracefully remove the drive from the system versus just scan the entire PCIe topology and hope that there's a drive still there. Another part of this that was important, there was no DPC or downstream port containment driver in the open source Linux. We have now contributed a driver to that effect, which is also an important piece from basically containing errors to a single drive and not allowing it to impact other drives in the system. If you're building a JBOF, you want to be sure, since it's shared across multiple hosts, that any error of a single drive doesn't affect any of the other drives in the system because, of course, those are still serving traffic. And then finally, it's important that you have a way to manage and monitor the SSDs in the systems themselves. So since NVMe is based on open source, we also wanted to make sure that we had an open source utility. So NVMe CLI is an example of that. It's already out there, and we're working with all of the SSD suppliers out there to ensure that their drives are actually compatible with the utility. That way we have a single management open source utility that can work with all the existing drives. So I mentioned earlier that we had to do some external PCIe cabling. External cabling is definitely a challenge when it comes to PCIe. It was never intended to be driven that far from the beginning. But we have found that by using mini SAS HD cables, so the same cables that have a proven track record with 12 gig SAS, actually work out quite well. To those cables, we've added a full complement of PCIe sideband signals, so the PCIe clocks, reset. We really want to continue to maintain flexibility in the topologies that you could build with this. Since there's still a lot of open work that needs to happen around PCIe clocking, for example, these cables will allow you to do that because the full complement of signals is still there. And finally, the cables are designed to be forward compatible with some of the upcoming PCI 6 standards. So one of the other interesting challenges that we had to tackle was to support different form factors. So we believe that M.2 is actually a very exciting option and a very exciting form factor at Facebook, so we wanted to be sure that we could actually use it in this context as well. So as many of you know, the challenge with M.2 is that, well, it's not natively hot pluggable, and it's also, the thermal density is quite a problem. So we've managed to solve both of those problems as well by creating a carrier design, which allows us to hot plug the entire carrier instead of the individual M.2s. We've confirmed that this already does work reliably. And then built into this carrier design, it also acts as both a thermal duct and or a heat sink, which really improves airflow over the devices and allows us to cool them effectively as well, even at very, very low airflows, allowing us to still build an efficient system around this. Ultimately, NVMe is definitely here today, and while there's still challenges that are being tackled, we do believe that we're close to having most of those solved. And so we believe that NVMe JBOFs are here and ready to go. Thank you.
Thank you, Chris. Now I'm going to turn it over to Don Falk with Intel. Don is a principal engineer at Intel, where he's been developing the server platforms for over 20 years. He's currently working on Intel's rack scale design, which he's going to talk about, and which really is about optimizing server, storage, and networking elements for deployment in large-scale data centers. So I'll turn it over to Don.
Thanks, Tom. So at Intel, we've been working in developing a pooled NVMe storage, primarily for the hot tier storage. And so before I get into that, I want to build some context around it. And so because this is targeted for the rack scale design leverages the pooled leverages the concept of pooled resources. And so we do that mainly by disaggregating the resources that are normally in a standard server platform like the storage and networking. We disaggregate those and then we create managed pools of these resources. And the whole purpose of this is to be able to compose systems that are tailored to the applications that are being deployed. So what this allows us to do then is to maximize the utilization of these resources on one end of the spectrum, and on the other end of the spectrum, it allows us not to leave stranded resources in the environment. And then also at the same time, by tailoring the composure of the system to the application, we can dial in on the performance that's required by the deployed application. And we do this all within a framework that provides interoperability. So if we look at the structure of rack scale design, we envision a multi-tiered storage structure. We have a hot tier, a very high performance, low latency hot tier, and then we have a fabric-based warm tier, and then which is primarily capacity and performance. But then, out further, we have basically capacity-driven storage, which is primarily driven by cost for capacity. With our hot tier storage, then we're kind of primarily targeting very close proximity to the compute, and also by introducing this hot tier and this warm tier, we can actually improve the performance of the applications. In the hot tier, then, if we were to look at this hot tier, and this is where we're targeting our application today, we're just a JBOF storage pool, NVMe storage. We're looking at our direct attached PCIe system with very low latency. And this is typically in the hundreds of nanoseconds or less than a microsecond of latency, plus the media. But we also expect full bandwidth capability. And then this tier is primarily driven by performance, or IOs per second bandwidth. But one of the characteristics of this, because it is a direct attached PCIe cabling, is that the radix is somewhat limited to 8 to 16 compute nodes. It's kind of our typical range that we're looking for in this. So what that does is that kind of pushes us, into, so this is a storage system within the rack, and the locality of that needs to be near the compute nodes. If we were to contrast that with, say, some of the NVMe over fabric pool, this is where we would see probably a larger radix. So if you're looking for systems or storage systems that want connectivity at the full rack level or multiple racks, probably the NVMe over Fabric would be a better connectivity model, but it doesn't provide quite the performance that we would have with a more local storage. Basically, this storage is capacity and performance driven, but the bandwidth is going to be pretty much limited by the Fabric attachment. But it does have very respectable latency with probably single-digit microsecond range of the Fabric plus the need. When we look at the system, then getting into further detail of the system, there's just kind of a simple block diagram of our architecture. One of the things that I want to point out is that we kind of make the choice of going with the dual-ported SSDs with active-active capability on each port. This provides a couple different things for us. One, it provides the ability to have multi-pathing to the SSD, but also with the dual port, you can attach to the drive with a Y2 PCIe Express lanes. What this does is this broadens your connectivity model, and what it does is it actually flattens the topology of the switch architecture within the system. The advantage of that is that when we look at composing systems, we think of locality of the resource and the elements within this. So when we compose it, because we have a flat, each port has connectivity to each drive. And so in the composition, I don't have to consider, well, do I have to go through the other switch to get to the drive? Each drive has connectivity to every port. Some of the trade-offs here was, with a by-2, you may think, well, are we sacrificing or leaving performance on the table from that connection standpoint? And in reality, a by-2 connection with 4K IOPS, with 4K blocks, we can get upwards of 500K IOPS with a 70-30 read-write mix ratio. So we felt that it was a good trade-off between performance and connectivity, and also simplicity in the PCIe switch structure. Also in this model, what we have is modular switch modules that allow us to service each module independently. And each module has a management CPU on it that manages not only the PCIe switch, but also provides a management structure to our pod manager, which is responsible for the composition of the systems. The management CPU has a gigabit Ethernet link to it, and so basically across there we run standard APIs, the Redfish APIs to be able to interface to the pod manager. The other thing that I want to point out here is looking at the cable connections. We're using the Mini-SAS HDD cables, using the 8644. Primarily trying to use the cable that's defined in the PCIe version 3 of the cable specification. So that's the system that we've been developing. If I look at some of the challenges, I think, again, you're going to hear this theme a little bit of the cables are bulky. When you do external attach for cables like this, we have bulky cables. And so there's kind of this trade-off between, how do you do cable management and serviceability? One of the things that, if I had any recommendation here, it would be, if you don't have to go for density, don't. What we try to do is keep the cables stationary and have the drives accessible from the front panel. It's a much simpler drive capability. And then the SSD, so basically it's a trade-off between density and serviceability. Host radix within the rack, one of the problems we had was, from a customer perception standpoint, when they see this, they want to be able to connect the whole rack. One of the things is that it is limited in its radix, and then so we would also suggest that if you need larger radix, you go over to something like NVMe over Fabric with a little bit of compromise in performance. Post-clocking requires SRIS. One of the things that we discovered is that repeaters need to be able to support this in order to have that. Otherwise, you're going to have to supply the clock over the cable. Drive telemetry, this is another area. Because we want to be able to compose system not only based on capacity but performance, it would be great if we could have a parameter within the drive that gave us some sort of indication of that drive's performance, whether it's IOs per second or bandwidth capability, but some sort of a metric that says this drive has this amount of performance. The tricky part of that is, well, it's probably not a single parameter that you need, and how do you characterize a drive in this area? So I think there's probably some work that needs to be done here. But if we're going to be allocating these drives based on performance, we also need a way to monitor and measure that performance. And so having read and write bandwidth capability, performance metric per namespace would be great, and that needs to be out of band accessible. So in short, or in summary, basically it's serviceability over density, understanding the radix that's required by the system, and then being able to monitor the performance of the drive at the target side is beneficial for us. Thank you.
Thank you, Don. Now I'm going to turn it over to Ziv Serlin from E8 Storage. Ziv is an expert in storage and networking architecture and solutions, both at chip and system level. His extensive background includes architecture and R&D management positions at a variety of companies, including Primary Data, a data virtualization company, IBM XIV, a scale-out enterprise storage system, and Comex Technology, building high-performance networking ASICs. So take it away, Ziv.
Hi everyone. I'm happy to be after Chris and Don, because for me, after Chris is like what I wish that I could be, and after Don, this is like the architecture that I would like to have. But I'm going to present maybe the actual that what we could build. So for explaining that, I think that I don't want to pitch about the product, although for us it's a very exciting day because we just launched the product and the company. But I'm going to maybe go over the key attributes that impacted the system that we needed to build for this product. So the product is built from a very high density. We need to support the 224 NVMe devices, of course with different capacity level, and that's future compatible to any capacity that will be able in the industry, and also touch a bit about that with different level of NVMe SSD that can be, for example, a 3D X point on NVMe and the current 3D NAND or eMMC and NVMe devices. We want to extract the full performance out of the NVMe SSD, and as an example, the current solution support up to 10 million IOPS random read 4K and 2 million random write 4K. And from a latency perspective, so we are the NVMe over Fabric, so our testing show that we added the 10 microsecond for the Fabric, and that's of course with our software features such as RAID 6 as an example. So beside that, the product itself is a tier 1 reliability product with a high availability, and we go into the architecture in a second of the system. But of course we need to support all the tier 1 reliability, and the product itself supports a lot of feature sets such as team provisioning, which is very critical, and RAID, as I mentioned earlier. So when we go into the system architecture view, So I have, that's the high level of the HA system architecture, and I wrote some points for myself to focus when we started to look on the system, and in our case we are focusing on using off-the-shelf hardware. So we are working with the industry. We are not trying to build the hardware by ourselves, but we are trying to with the relationship with different vendors, from the SSD to the network to the enclosure itself, to define and to leverage what exists in the industry. And that's part of the challenges that we are facing and we face doing this product. For HA product, and to be honest, when we started the product, we said that it's very easy. You just take an SVB, which is a SAS, you need to replace the SAS with the PCIe, and that's it. So that's what we said, but when you go to the practical, you understand that there is a lot of challenges around that when we are working with the product, because if you want to do a passive mid plane with the PCIe, it's much, and the traces are much longer, it's much more tricky and sophisticated if you compare it to a SAS when you have a SAS expander or SAS controller. And of course, you always need to maintain the most single point of failure. Of course, there are some things that you can leverage from the existing, you can say even SAS solutions such as power control and power protection. But even here, you need to think about how do you maintain the 25 watt, as was mentioned earlier, for each PCIe SSD, and if you want to power control that, that's unique features as well. All the management interface, which is still in development under the NVMe, that's something that you need to be supported on the platform. There is a lot of improvement over there, but still there is a major change if you look on the management interface between SAS solutions, as an example, to the NVMe enclosure that we used. And node-to-node communication, this is very critical, at least in our cases, because we don't want to capture or allocate a lot of the bandwidth between node to node. We want to leverage as much as we can from the PCIe interface for our performance or for the customer performance. When I go deeper into just one of the motherboards as an example, this was very critical for us and very hard for us to establish at least 1.5 years ago in the market. In order to, so we are based on the fabric, and for that we needed a network on one side and the SSD on the other side of the solution. And when I'm saying network, it's pretty much RDMA network card. And for that, we need to make sure that the system is very balanced. And when I'm saying very balanced, there are two main points that we focused, two main areas that we focused. One, between the network and the SSD. For example, a lot of the motherboard design, you can get a lot of bandwidth towards, for example, the network, but not a lot of bandwidth towards the SSD, or vice versa. Another balance that we were focused about is the QPI. And that's the interface between the two CPU and dual socket motherboard. The idea behind that is with our software architecture, we are focusing on using a low-cost CPU that the QPI bandwidth or frequency can be a low QPI frequency, and we wanted to make sure that our architecture will not be bottlenecked by the QPI interface. So specifically with our software architecture, we can basically use the system without using the QPI interface between the CPU, and that was not a bottleneck for us. BMC management, this is very critical because in PCIe enclosure, the BMC is taking a lot of the management of the system. When you're designing for a tier 1 reliability with HA, you need to make sure that the BMC do a lot of error handling and management of the platform, specifically on the PCIe, around the PCIe SSD. So there's a lot of work that need to be implemented, need to be coded into the BMC, and there are still a lot of differentiation between different enclosure vendors. So we need to do a lot of features together with the vendors. Surprise removal, surprise insertion of an NVMe SSD. So I think it was already mentioned almost in the three sessions, three lectures before me. And that's also, for me, it's something that it's good that we have all these panels because see that at least myself, I see that all these issues are, all others face that as well. And error recovery and also error reporting. Error reporting, we just faced a lot of work around that. There are still a lot of utility and that can be done, I think, in the industry level to report even from a correctable error or uncorrectable error around the PCIe, and that today we are doing by ourselves, not a lot of utility around that. Okay, so a bit about the future. When working with the vendors for the last 2 years, I think that there is a lot of movement around the PCIe. A lot of the devices will support PCIe from the network, from SSD, of course, from chipset, and the system needs to be much more flexible and configurable. Today you can see a lot of different flavors of system, and at least from a vision perspective, it needs to be a PCIe fabric switch that can support the different options per customer need. That's, I think, and this is maybe my last slide that maybe summarize the changes that we saw in the last, when we ramp up the system. So it was even from a physical perspective of the interoperability that the vendor need to do in order to test system level. Power recent sequence in a dual port environment, this is very tricky. Surprise removal, surprise insertion, I think it was mentioned. BIOS is very critical when you're working with a lot of PCIe SSD. What happens, for example, when you do a surprise removal when the BIOS is booting up, you can try that. And cooling power and power protection, I also mentioned. So thank you very much. That's my slide. Thank you very much.
Thank you, Zip. So I'm going to turn it over now to Tim Emami from Network Appliance. Tim's the subject matter expert for all things SSD and HDD, supporting all the business units at Network Appliance. His role is to call out emerging technology trends and then help to guide and transform those trends into market opportunities. He's actively participated in all of NetApp's flash deployments, be it SATA, SAS, PCIe, pre-NVMe PCIe, and now NVMe PCIe. Prior to NetApp, he developed storage devices at Maxtor, Quantum, Western Digital, and StoreCard. So I'll turn it over to Tim.
So, I think I'm the last guy here between you and the beer and pizza, so I'll try to move along here. I think as Luke pointed out, kind of going last is sort of good and bad. You could say all the good stuff's been covered, but it's also nice to know that we all have the same sort of problems, right? So, yeah, so I think, I'm coming from it from sort of the, sort of the traditional, SAN-based storage appliance kind of, right? And really, I'm making a pitch here for, and really, I think that's sort of evolving to become these all-flash brands, right? Where you're sort of selling a general-purpose solution, right, with flash in it, right? And traditionally, this has been served by, very much historically with fiber channel SAN, more recently with sort of these boxes, right, that are attached various ways, but present typically in block storage, right? And really one of the important elements of this, which is kind of a carry forward, right, is this notion of internal sort of parity or redundancy protection, right? That's important for a number of reasons in that sort of SAN environment, call it, right? So I think the dominant thing here is sort of this this notion of parity rate economics, right? We're going to have this sort of internal redundancy, right? Then that sort of arguably colors or influences the kind of SSDs that you need. And so the top line, I'm making this sort of making the case for, all flash arrays need value dual-ported NVMe SSDs, right? Something that, isn't there now, right? As in, the first wave of dual-ported NVMe SSDs are, I would say, have missed the mark, right? So really, carrier rate economics kind of drives us towards this lowest dollars per gigabyte, right? This kind of this data center grade NAND, which is kind of the opposite of what, sort of the initial wave of dual-port SSDs come with. And we're going to take these things and aggregate capacity and performance, right, in the node, right? And therefore, sort of we have slightly different requirements than, let's say, some of the server guys, where we have much fewer devices, and we kind of want to get, all of the performance out of it, right? And then just one little point about, I guess, how is RAID going to evolve to deal with, SSDs, and specifically some of these larger SSDs we're hearing about. Well, I think we sort of need to change the way we sort of look at the problem, right? I think a lot of it is really not thinking of these sort of failure modes as all or nothing, right? But in fact, with so many elements, I think is what folks are calling it these days, inside of an SSD, for very large capacity, it could be, 1,000 dies, right? So what do you do if a die fails, right? And historically, you've just chucked it over the side and start to rebuild in something else. Well, we're not going to be able to do that. We're going to be able to afford to do that for a whole number of reasons. So there's quite a bit of discussion in the standard bodies around, why not really sort of change the way you view this and, kind of use what's still there and working, and right? So that really needs this repair in place, to deal with a shrunken capacity device and keep it in operation. The other thing is sort of this notion of, peak performance isn't that important to us. I just had this little, kind of cartoon on the side. We just collected some data. It turns out there's some interrupt coalescing going on, so kind of ignored the bottom end there with the SAS. And I'm not going to reveal anything about where this comes from. But the main point here being, we're not interested in sort of the end of the curve here on NVMe, right? We're interested in that sort of region that we've outlined, right? That's where we think the value of sort of NVMe lies for, specifically for these all-flash arrays that are on the other side of the wire, right? To get, a significant latency reduction at lower sort of concurrencies, right? And not about sort of bleeding edge IOPS. And then obviously, sort of traditional sort of view forward from, so let's say SAS or fiber channel, so we still need these high availability configurations with no single points of failure. That really means dual ported NVMe. We need, PI and SQL support. We need namespaces and namespace reservations. We're planning on taking, and the other, way to drive the parity costs down, taking these SSDs, building them into, let's say, traditional, I'll call it a 10+2 RAID group, and then being able to partition and slice that capacity and share it between multiple nodes in order to reduce the overall cost of parity, right? And namespaces are an important part of that. We're glad it's there. It gives dual-ported and value dual-ported NVMe SSD that we need overlaps quite a bit with what we see sort of emerging for NVMe over fabric, right? And I think as somebody pointed out earlier, Dell really created these islands of flash, right, and made it harder to correctly sort of provision the amount of fast memory to compute, etc. Right? And I think NVMe over fabric, promises to break that barrier. So obviously, I think we've all seen this data that suggests that the cost of remote versus local access is going to be much, much lower. Obviously, you have to use the right fabric. And this really addresses a lot of the traditional bottlenecks in OS, with the way the drivers are laid out, right? And also, I think, besides that, sort of disaggregation, which, really, there's a separate thing here around redundancy models, right? We can sort of disaggregate and still do, multi-copy replication, erasure coding, or, the other thing it can it can do for, let's say, more traditional use cases is this notion of scale-up expansion. SAS is really good about for expansion, NVMe isn't so good. And we think that that probably will evolve to be a form of NVMe over Fabric, right? So basically, NVMe over Fabric needs the value reported, all of the same things that the value reported NVMe SSD needs, plus these other things, just control of memory buffer, SROV multi-namespace, and then I think the clocking, right, really needs to be addressed. I think that's going to be a problem. And it's a little late because as we're sort of looking at what to build, let's say, for middle of next year, the fact that the clocking hasn't really settled is kind of a problem, right? I mean, if we're going to build a high-density enclosure 2U24, 4U48, whoa, that's a whole lot of clock planes. So anyway, so we're trying to deal with it the best we can, which is kind of hedging our bets, maybe laying the stuff out, maybe not driving it, kind of seeing where the thing lands, right? And then this thing here, which, I'm really glad that things are kind of starting to sort of take off here, but I hate to say this was a little bit of an afterthought, right? And partly because I think the folks who were sort of driving the NVMe forward initially, really thinking about it as much more of, hey, I want this to be close to CPU, and that's the main value. But as we move forward here, we're finding that there's a serious gap here, right? SAS had SMP, right? It was sort of designed from the get-go for enclosure services. Well, at get-go wasn't pretty early on, right? And here we're, and to kind of make matters worse, you sort of have different folks with different requirements, right? The direct attach guys, the server guys, and then the storage guys. Each one sort of used to doing this a slightly different way, and so it's a little bit of a mix at this point, in order to kind of figure out how this is all going to play out, and we're kind of trying to engage and drive it, certainly drive our requirements. One of the things that we're actually making a plea for folks here to hopefully help us support is, we're finding that we don't have a, like a SAS has this power disabled function, right? It's a pin you can drive, pin 3 or pin 9. But that isn't there in NVMe. We think it's a big deal because if we don't have that, then we're going to have to put a FET somewhere, right? So we have a TPAR. It's going to come up for discussion on Thursday. Please consider supporting that. I can move a bit of a thing. And then finally, I think this is my last slide. Yeah. So, I think tiering actually becomes important again, right? So this is like, we started with sort of tiering because flash was expensive, right? So put all your hot data here, right? And really the initial hybrids are all about making the overall cost of the IOPS lower, right? Use a little bit of flash, use the disks, and pretty much deliver fairly forecastable workloads a significant performance boost, right? And the flash got cheaper, like talking about all flash arrays, right? But I think, certainly with the emergence of storage class memories, right, which are going to be quite expensive, you got to start thinking about, well, does it make sense to tier and be able to effectively, and of course there's always the hard drives, which I think if you saw the Facebook keynote, there's still a place for them, because if that gap remains too big and your data's cold enough and the apps is good enough, right, why pay a penny more for, right, TCO on this very cold data that's probably hard to monetize, right? So hybrid of the future is going to be a very different thing than sort of the hybrids that we first had, right? And it's not about IOPS efficiency. It's really about driving this total cost of ownership down, and be able to stitch together probably these 3 tiers, which have very different characteristics, and also be able to scale those independently, right? The rate of data growth, right, for A, B, and C is quite a bit different, right? So philosophically, we think we're not going to be building these sort of integrated boxes that are hybrid, sort of make guesses about what the ratio of these things are. Much more likely for, let's say, private cloud or a bunch of significant use cases. You need to be able to scale the hot tier completely independently from the cold tier, because they're growing at very different rates. And I think that's it for me.